Let's take a look at some practice questions related to probability distributions. Our first question deals with uniform distributions. The question asks us, a standard 12-sided die is rolled. The player wins the dollar amount equivalent to the value on the die. The cost to play is $6. Using mathematical models from this unit, determine whether this is a fair game to the player. You must mathematically justify your claim for full marks. And the idea here is that we're going to want to find the expected value. So how much money is a player likely to earn? We want to consider how much it costs them to play, and then decide if it's a fair game. Fair is whether there's, a realistic chance that they're going to win money, or are they just going to lose money. We've seen that for some distributions, there's kind of a shortcut for the expected value, but not with uniform. So with uniform, when we're going to find our expected value, so EX, it's just going to be our traditional formula that we've started with, I equals 1, and so we're going to find the product of each value for the random variable and multiply by its probability and then find the sum, and that'll be our expected value. So let's set up our distribution first. So we're going to have our x and our p of x, and might as well right away add the column for the product. And let's define our random variable x. What does it represent? So we will say let x represent the number shown on the die, which is also the amount of money earned in dollars. So dollars earned in the turn. So we know that our possible values for a 12-sided die are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. What is our probability? Well, it's a die, so we know from previous experience and just general discussion that there's a 1 in 12 chance of winning. We also know this is a uniform distribution. All the probabilities are going to be the same. So in each row, the chance of winning is 1 out of 12, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. We could do a sanity check and sum these up and make sure that our probability equals 100. In this case, I just did 12 entries of 1 over 12, so I know right away that it's going to be 12 over 12 or 1 or 100%. So I don't need to actually do the math there. But for more complicated questions, it's good to double check. And let's find our xpx. So we're just going to multiply across. So I'm going to have 1 over 12, 2 over 12, 3 out of 12, all the way down. 4 times 1 over 12 is 4 over 12, and 5 over 12, and 6, 7, 8, 9, 10, 11, and 12. And let's sum those all up. And when we do that, we find that our sum of all of these, so sum is equal to 78 over 12, which we can simplify to 6.5. All right, what do we know about our expected winnings per game? So like what's our net profit? So we can express it that way. So net profit per turn is our expected value, so our earnings minus our costs. How much are we expected to earn in each turn? Well, 6.5. So expected value is how much we expect, or the average amount that we will win on a given turn. So $6.50 minus how much are we spending to play? The cost to play is $6. So minus $6. Oops. So the expected net profit per turn is 50 cents. So is this game fair? Yes, it's expected that most of the time they would actually win something. So in some ways, if you're the person offering this game, you haven't designed it very well, because overall you're going to be paying out on average 50 cents per turn as opposed to earning money. Let's finish off with the concluding statement. Therefore, this is a fair game because on average players will win 50 cents. Or like, I guess we should say profit by. So they'll win $6.50 for their $6 investment. Our next question relates to the binomial distribution. Just to start off, I'm going to write the formula for binomial off to the side, just so I can remember which variables I'm going to need to consider and define as I answer this. So NCX, P to the X, and Q, or 1 minus P, however you want to think about it, and minus X. And expected value in these situations is just going to be given by N times P. All right, let's read our question, let's identify our variables, and let's go ahead and solve. An advertising company has found that it has a 35% response rate to their advertising flyers. The company samples 10 people who saw their flyer and asked each person if they responded to the flyer. What is the probability that exactly 4 people responded to the company's flyer? So let's decide what success looks like. We're going to say let X be the number of people who responded to the flyer or to the advertisement. And in this case, we are asked to find what is the probability that exactly 4 people responded to the company's flyer. And so we're finding the probability when X is equal to 4. All right, we are having 10 trials here, 10 people that are being asked, and these are independent trials. The response of one person does not affect the other. These are all totally independent individuals. We're testing for X equals 4, so we're asking, or we're looking for 4 successes. The probability of success is given right here in the question, 35% response rate, so P is equal to 0.35. And Q, which is our failure rate, is equal to 1 minus our success rate. And so that's going to be equal to 0.65. Let's plug those numbers into our equation. So probability that X is equal to 4, or the probability that exactly 4 people responded to the company's flyer, is N, which is 10. Choose 4. So how many different ways can we choose arrangements of 4 times the probability of success? 0.35 to the power of 4. So how many people, basically it's our success probability and our number of people who count as a success, times our failure rate, 0.65, and how many people are left. We started with 10, we've already asked for 10 minus 4 is going to give us 6. Oops. And let's do that calculation right away and let's see what we get. And when we do that calculation, we get an answer of 0.2376, so we'll round to 238, or in other words, 23.8%. So therefore, the probability that exactly 4 people responded is 23.8%, approximately. And then question B says, what is the expected value? Give a proper interpretation of this value. Well, we already know our variables here. I know that N is my number of people asked. That was 10. My probability is 35%. And my expected value is what we're going to find. So we know our given and required. Let's sub our numbers into our equation. E of X is equal to NP is equal to 10 times 0.35, and that's going to equal 3.5. Now let's remember, E of X is basically the expected or average value of our random variable X. And we set up here initially that X is the number of people who responded to the flyer. So, therefore, the average number of people who responded to the flyer is 3.5. And that's 3.5 for every 10 asked. So maybe we should be a little more specific. So therefore, in a group of 10, the average number of people who responded to the flyer is 3.5. Our last question in this practice test is hypergeometric. Once again, to start, I'm just going to write the formulas off to the side just to help guide me as I set up the problem and as I read through the word problem and look for important details. So P of x equals ACX, so our successes, times n minus a, choose r minus x, that's my failures, over NCR, which is my total number of ways of choosing in this situation. The question tells us that Mr. Harris has decided to randomly purchase pet fish by removing 3 fish from a tank at the store. So he's going to go to the store, go to the tank, and choose 3 fish. The tank has 10 guppies, 8 goldfish, and 3 mollies. What is the probability that Mr. Harris will get a goldfish or 2 mollies? So we're finding the probability of 2 goldfish or 2 mollies. And it's an or question, so that means that we are going to add. So we're going to find the probability of 2 goldfish plus the probability of 2 mollies. Now the question is, how do I find the probability for each of those events? And well, that's when our hypergeometric probability formula is going to come in. In each case, we're going to need to define our variables and decide what success looks like. So in the first case, we're just going to deal with the goldfish. So I'm going to define my variables off to the side here. So A is the number of successes in like the population that I'm choosing from. So right now, actually, we should say let X be the number of goldfish. So right now, success is being a goldfish. How many successes are there in the tank? How many goldfish are there in the tank? There's 8. How many are we choosing? Well, it says that we're finding the probability of finding 2. So our number of success is going to be equal to 2. N is the total number of items in the population. So in the tank, we have 10 guppies plus 8 goldfish plus 3 mollies, so 21. And finally, R is how many trials we're performing. And it says we're removing 3 fish from a tank. So how many trials are we going to perform? We're going to perform 3. Now let's plug those numbers in and see what we get. So we're just working with the left side of the equation to start here. So ACX, so there are 8 possible goldfish, and we are finding the probability of choosing 2 times. How many are there left to choose from? Well, there were 21 total. We've already eliminated all the goldfish, 8. So 21 minus 8 gives us 13. Choose, and R minus X, how many trials did we perform? Well, R was 3, X is 2, 3 minus 2 is 1. And on the bottom, we need the total number of ways to select our fish here. And we know there are 21 total fish in the tank. We are choosing. The order doesn't matter. We know it's choose because I just care in the end how many fish of each type do I have, not was the first fish a molly, was the second fish a goldfish. We don't care how they were selected. We just care about the end result. And how many trials did we perform? We removed 3 fish from the tank, so that's going to be 3. Let's work with our next term now with finding the mollies. So in this case, let X be the number of mollies. And very similarly, A is our total number of successes in the population. There are 3 mollies in the tank, so there are 3 that we are choosing from. N is still equal to 21. That's the total population of fish in the tank. X is equal to 2, so success is selecting 2 mollies. And R is equal to 3. That's our number of trials. That's 3 fish we're moving from the tank. So we have 3 attempts in order to select our 2 mollies. So let's plug our numbers into our wonderful hypergeometric probability equation here. So it's plus ACX, so A is 3 mollies in the tank, and we want to try to choose 2, times how many fish are left in the tank. 21 minus 3 is 18. Choose, so out of those 18 remaining fish, we're choosing 1 to have our total of 3. And once again on the bottom, how many different ways are there to choose fish from this tank? There are 21 fish, and we are choosing 3. And now it's just a matter of calculation, so let's jump to our calculator and calculate these values. And in the first instance, we're going to get a value of 0.274, or if we stick with the fraction, 26 over 95. Let's find our second value. And we're going to have 0.0406, or 27 over 665. And we notice that the probability of choosing the mollies is a lot smaller, and that's not really a surprise. In each case, we want to end up with the same amount of fish, 2 goldfish or 2 mollies, but there are 8 goldfish in the tank to choose from, but only 3 mollies, so obviously we expect that the probability of selecting 2 mollies is going to be lower. All right, let's finish adding this up, and let's see what our final probability is. And when we do the math, we get an answer of 11 over 35, or as a decimal, approximately 0.314, or 31.4%. Looks good to me. Let's write our concluding statement. Therefore, the probability that Mr. Harris will get 2 goldfish or 2 mollies is 31.4%, or approximately 31.4%.